Okay, let's get ready for lecture. I want to we left off calculating frequencies. Let's do another one for 550 nanometers. And I'm going to give you one on the iClicker in a few minutes. All right, so let's do this calculation again. Do it carefully. And get your calculator out. And on Tuesday for exam 3, definitely bring your calculator because you may not use your cell phone for any reason during an exam, midterm or final. And you're going to want to use scientific notation. All right, so let's do another visible wavelength, 550. That's kind of greenish blue, I think. And let's calculate the frequency. Now, as before, we take the basic wave equation, C equals lambda F. And we get the lambda over to the other side, and we get F by itself. Now, that's this equation up here in the first equation block after the arrow. C over lambda equals F. Now, if we want to calculate a wavelength from a, say I want to set a frequency, okay, like WDBO 580 kilohertz, 580,000 cycles per second, then I put it in the denominator over here, and then I can figure out the wavelength from that. So that will help me design the antenna for WDBO, so that they can transmit, because the size of the antenna depends on the size of the electromagnetic wave you're generating. All right, so here we go. Let's calculate it. Now we're going to do it out step by step. And the steps that we're going to do right now are going to be similar to the steps that you'll do in a few minutes on iClicker. Okay, so don't let me catch you napping. All right? I'm just checking to see if anybody's napping. Nope. Everybody's ready to roll. Let's go. All right, so F equals C over lambda. Okay. Lambda's in the denominator, 500 nanometers. And remember, a nanometer is the same as 10 to the minus 9 meters. Now that's in the, and we got 550 of them. So that goes in the denominator. All right. And then the speed of light, that's always 3 times 10 to the 8. It's a constant of nature. 3 times 10 to the 8 meters per second. And I think in the English, it's a, this is funny. The first way I ever heard about the speed of light was this. 186 million miles per hour. No, 186 million miles per second. I think that's what it is. So per second, it's really, really fast, no matter how you slice it. All right, there's our calculation. Now, one of the things that I forgot to mention last time is cancel meters top and bottom. Well, I mentioned it, but I didn't have it in the slide. So cut out those meters. Now you still have per second up in the numerator. That's all right. That's the unit of frequency. So many waves per second. Or as we say, so many hertz, Hz. All right? So now, if you're going to do it on pencil and paper, like we gave a midterm for astronomy the other day, Tuesday, and a bunch of students in there, they forgot their calculators. So they had to do a couple calculations, not too bodacious, but they had to do it on pencil and paper. So if you're doing it on pencil and paper, this is what you got to do, or something like this, depending on how. This is how I would do it. I simplify my powers of 10 so that I only have one power of 10, 10 to the something power. Now 10 to the minus 9, as I said last time, down in the denominator is the same as 10 to the regular 9 in the numerator. All right, so that means now I've already got 10 to the 8 up there in the numerator, and now I convert 10 to the minus 9 in the denominator into 10 to the regular 9 in the numerator. So now I've got 10 to the 17 effectively in the numerator. All right, but I still have 3 divided by 550, so I got to deal with that. All right, so now if you're doing it in your calculator, and hopefully you have figured out how to do this, because I was trying to, I don't know, somebody I was trying to show after class Tuesday. This is how you would do it on your iPhone calculator. Now you tilt it sideways so you get the full scientific control panel. And you can do 3EE17 divided by 550. Now that'll give you the answer, right? But we're not going to do it that way. The quotient 3 divided by 550 is the same as this one. Okay, so that's this decimal fraction over here. And I haven't done anything with the 10 to the 17 or the 10 to the hertz. Not yet. All right, so 3 divided by 550, you know, that's about 6 divided. So this is about 0.006, 0.005, somewhere in there. You do it out on your calculator, yup. 0.00545454545454, blah, 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 de blah. All right, it's a repeating decimal fraction. All right, so just write down a few decimals. All right, and we still got that 10 to the 17. Now, 10 to the 17, if I move it 3 decimal points, this is true scientific notation here. All right, but it's not, I don't have my answer in terahertz yet. And your calculation on iClicker in a few minutes, we're going to have to do it one more step after this. But if we were doing a written exam, you know, like the Physics 2048 for scientists and engineering students, and all those engineering majors over there, and you know, engineering majors, they're a squirrely lot. But in those exams, we give a lot of written work. So I'd take either of these and say, yeah, okay, they got it. But for us, we're going to be clicking stuff in with iClicker, so I have to specify. So I go from 0.00545, move the decimal place 3 units in to the right, and decrease 10 to the 17 by 3. So 10 to the 14. Right? So that's a true answer. Right? And you know, if I wanted to do scientific notation on a test, okay, whether you're an engineering major or whatever your major is, I could have you type in the letter E and then 14 in this case. And that would work. But usually I'm going to try to give you an answer, or ask for an answer in terahertz. Here it is. Move it 2 more decimal points to the right and decrease the powers of 10 from 14 down to 12, another 2 powers. And that is why you're allowed to move the decimal point another 2 points to the right. And 10 to the 12th hertz is a terahertz. And you guys, I'll write a bunch of those prefixes on the cover page. So I'll have, everybody knows kilo means 1,000, 10 to the 3rd. And mega means 1,000,000. You know, like mega million, lottery. So mega million means mega means 1,000,000 and 10 to the 6. Okay. Giga, capital G, stands for 1,000,000,000, 10 to the 9. And tera, capital T, stands for 10 to the 12. So I've got it where I want it now. Okay. And, you know, I could have stayed up there. I don't know what the next one is above tera. I think it might be yada or something like that. You know, yada, yada, yada. Can't remember what 10 to the 17 is. But anyways, I'll look for answers in terahertz. And usually I'll ask you to round it off to the nearest terahertz. So then you type in 545 on this one. All right. And just to review with you this scientific notation. Well, let me ask for questions here. Anybody have a question? Go ahead.
So all of that is required in exam. You have to go all the way down to terahertz.
If I ask a question like this, I'm going to tell you terahertz. But if I give you a different wavelength, it might be gigahertz. Okay? And so you'll have to, instead of cutting it down to 10 to the 12th, you'll have to cut it all the way down to 10 to the 9th. And you'll see it, but I'll tell you on the clicking page, okay, give me an answer in terahertz, or give me an answer in gigahertz, or AM radio, give me an answer in kilohertz. You know? Question.
So 10 to the 12 hertz is terahertz.
Correct.
Need to remember that.
No, you don't need to. The student up here said, so 10 to the 12 hertz is terahertz, and we need to remember that. But the answer is no, you don't need to remember it in terms of memorizing it, because I'll have that on the cover page. Okay, but you do have to know how to work with it, all right, which is what we're doing here. Okay, one more question.
So on the
Wait a minute, you're supposed to say, if it please the court, or your honor.
Your Honor. Okay, the 5.
Overruled. No, I'm just kidding.
5.4545 times 10. You move the decimal point 2 places and then subtract 2 from the exponent because you moved it 2 places.
Right. Mm-hmm. Yeah. Every time you move the decimal point to the right, the power of 10 has to dip by that many decimal points. Yes.
So that 10 to the 17 will be constant in each equation because of that negative.
No, it won't be. It depends on the wavelength that I give you. So for instance, WDBO is going to be a very long wavelength. Okay, that's 580 kilohertz on the AM dial. And that's measured in meters, not nanometers. Okay, so, but, you know, so think of it this way, like the young lady up here, if it please the court. When you move, if you move the decimal point, whatever the numbers are, you know, get your numbers squared away, and then move the decimal place to where you want, and then, you know, so for every decimal point you move it, dip that 10 of the whatever by 1.
So the negative 9 can change, but the 3 times 10 to the 8 will stay the same.
3 times 10 to the 8 is always the numerator for light. Okay. Now, if we were doing if we were doing sound waves, you know, like sonar or music, you know, that would be like 343 meters per second up there. So that'd be, you know, you wouldn't even use scientific notation for that. But for light, yeah, it's always any kind of electromagnetic radiation. So visible light, radio, infrared, ultraviolet, X-rays even. And X-rays have wavelengths in the single and fractions of a nanometer range. So they're very tight wavelengths. Okay. Another question. Yes?
So how do we get the scientific notation for the denominator, so the 10 to the negative 1?
Well, you get the scientific notation for the denominator from how I state the problem. Okay, so I'm telling you, for our example today, if it please the court, we will do 550 nanometers. So as soon as I say nanometers, you should think 10 to the minus 9 meters. Right, now if I tell you millimeters, okay, IQ test question. If I say millimeter, you know, like 7.5 millimeters wavelength, What's my power of 10 in the denominator? 3? Negative 3. Right. Okay. So you have to read. You know how I always say read carefully? Now you know why. Another reason to read carefully. So, but I'll always state it somewhere, and then you got to put it together in the denominator down there. You know, millimeters, nanometers, kilometers. Then you'd have a 10. You know, and there's students, the U.S. Navy uses extremely low frequency radio waves to communicate with submarines at sea. And they have very long wavelengths, you know, hundreds of meters and kilometers in length. So their antennas are really, really long. And they're not vertical, they're horizontal, you know. And because those waves penetrate seawater, you know, to a good depth. But you know, visible light, it's going to be it's going to be 400 to somewhere between 400 and 700 nanometers. So, but you know, theoretically, you know, there's a whole range of wavelengths. Okay, another question here. It's all right, don't apologize. The question is, nanometers, that's like 10 to the minus 9 and stuff. Are you going to have that on the test? The answer to that is YES, yes. It's going to, I've already said it about 15 times today. It's going to be on the cover page. Because I know a few of them by heart, but like anything above giga or below nano, I got to look it up myself. So, you know, like femtometers, yottameter, you know, there's all kinds of prefixes and stuff. But from 10 to the minus 9 to 10 to the 9, I'm good. But other than that, I have to look it up. So I don't expect you guys to memorize it either. So I'll just put it on there, you know, because it's the thinking. It's, you know, scientific notation is not that interesting, right? It's a tool. So I'm going to give you a toolbox on the cover page. Good. And then what you do with it, you know, you can make, you know, a beautiful chair, or you can make a tree house, or you can make a wooden spoon, or, you know, anything that you want, or toothpick, you know, out of wood, you know, so it's depending on what you got to do and the tools that you have. So, another question. All right, let's go past this one. We've already done that. All right, here we go. Calculation time. 410 nanometers. This is violet. And can you bring the lights up to 100%, please? All right, so just take a few minutes and calculate. Double check with your neighbor. Make sure you're not blooping it up. We just went through it. And now, what is your name? Mackenzie? Mackenzie, see how I say type in the numeric part of your answer to the nearest terahertz? And then I give you an example of how to round it off. I'll do the same, almost the same wording on the test, except I'll also type in. Actually, it will be the same because it'll be on the click. If I have a question like this on the test, it'll be clicking, so you'll have to hit the send key. So it'll be just like this, if it's on the test. Now I'm not telling you what's on the test, but I can't do that. Round off carefully, you guys. Do not let me catch you napping. Now I'm starting to get nervous. Dare, do you have a calculator on you? Wait a minute, I'll use my phone. Never mind. Round off carefully, my wonderful students. Do not let me catch you napping. Let me hydrate up a little bit. Dear. What was that? You had your tongue up like this.
I do that sometimes.
You do?
Yeah.
When you're focusing?
Yeah.
So, are you, is it allergies and stuff that is,
Oh no, I had like a stomach virus over the weekend that I got from my mom.
like flu poisoning or food poisoning?
I don't think it was food poisoning. Like I think it was an actual virus because she had it and then like right when she was finishing it, I got it.
Nice.
And then Monday I have rehearsals until.
Because that'll wear you out
Yeah.
too. I mean, it
Yeah.
dehydrates you.
Yeah.
Something pitiful.
I have rehearsals until 10 o'clock all but one night this week. For the
Till when?
Till 10 o'clock.
Oh my goodness.
And so Monday I was like, oh, I'm fine. It's okay. I'll deal with it. And then Tuesday I woke up and I was like, I overdid it. I feel horrendous. I was like, I was not 100% better. So now I'm mostly just tired.
I was worried about you actually. But I knew that your puppers would take care of you
You take care of it.
because they have to stay on guard duty. They guard you, plus they make sure that there's plenty of treats, or they make sure there's not too many. If there's too many treats, they eat them. Right? And if you have treats, your treats, they eat those too. Whatever they can persuade you to share. Yep, that's the way hound dogs are. The world over. Small, big, doesn't matter. Okay, what do we got? 97. We got more than 97 here. Did you see this? You know how much this cost? $4 at CVS. And plus it has little pouches. So I could put, like the chip in here actually. Plus it has these little slots over here. I think they used to give these away for free because when I went to check out, the lady said, I don't think it's for free. I said, well, it says $3.99 back there, so that's what I was figuring to pay. So, okay, one more minute. Ooh, the red high tops. Very nice, Shanice. The red high top sneakers, very good. Plus it coordinates with the rest of your outfit. I saw somebody else wearing Converse. I don't know where it was. "15 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. Raise your hand if you typed in 732. Very nice. And for those of you that typed in 731, you got caught napping. Now here's the calculation. All right. Thanks, dear. We still have more, so don't turn that off yet. 3 divided by 4, 10. Then my 10 to the 17. So 3 divided by 4, that's going to be about 0.07. So 0.007317, and I think that one repeats as well, if I'm not mistaken. All right, and so you figure that one out. It's 731.7, but to the nearest whole number of terahertz, 732. So Kisla, did you get that one? Sweet. So if I give you a lot of these on exam 3, that would be nice. Perfect. Nice. Good. Okay. Good. I like to hear that. Now, let's continue with some more discussion about waves and especially wave interactions. Now, last time we had a picture, a real photograph of waves, and in the photograph, the waves were moving vertically upward. I mean, it's an overhead view of something going left to right, but in the diagram, it was vertically upward. And then it hit a gap in a barrier, and most of the waves could not penetrate the barrier. But the ones that hit the gap, they went through the gap, and then they seemed to curve outward in a spherical array. And that's what we call diffraction. And in the gap, we think of the gap as being a source of wavelets. And down the line, those wavelets form this. And now this is an idealized view, right? This is kind of a schematic diagram. But the one that we saw last time was a real picture. All right, now I've got a couple other pictures here from the ocean. All right, here's one. All right, now take a look at that one. And if you keep your eyes open, now that you know what to look for, you can see diffraction all over the place. Here's another one. Look at this. This is a radar. This is basically a radar image from a spacecraft up in orbit of the ocean. And, you know, I can't make out exactly where that is. But I think it might be somewhere down in Indonesia or something like, you know, down where all those islands are by Indonesia and Java and stuff like that. And you can see the waves now down here in the lower right, they're all kind of moving to the northwest. They're moving toward those islands. But now look over here on the other side of the islands. Look at that. They've changed direction. And see down here? They're very close to being parallel lines down here in the lower right. But up here on the far side of this island here, those look like circular waves. All right? So that's diffraction. All right? And we get some circular waves over here. And so here's your gap right between those two islands. All right? And that's diffraction. So here's a question. What you're looking at there is a gap between two islands. So now a question is, what's the opposite of a gap? Well, a gap is an opening, free passage of waves, surrounded by two areas where they can't penetrate. So the opposite of that is a small size object that they can't penetrate, flanked by a wide open space where they can. Right? So, for example, here's an object that's called, in the modern day, this is called a baseball. In the days of Sir Isaac Newton and those guys, it wasn't even invented. Right? But it's a sphere. Right? So here's our question. how does that train of waves over there to the left, let's say they're moving left to the right, so I gave it an arrow. How are they going to interact with this Newtonian object, a ball? I'm sure that Sir Isaac Newton, I guess they probably played cricket in those days. Cricket, soccer. They didn't play basketball, but I'm sure they had all kinds of games, and marbles, so they had spheres and stuff. This is a common everyday sphere of baseball. So what do the waves do when they interact? And look at those waves. They're moving from left to right. Right? Now, eventually, that set of waves is going to strike the baseball, and then what's going to happen? Are they going to go by on the right or go by on the top, go by on the bottom, and stop everywhere else? What's going to happen? Let's take a look. All right. Now, here's the baseball. All right. So, are we going to get a shadow? Go ahead and sketch in a shadow. Sketch in this. Definitely sketch this in. A set of parallel waves, like the waves in the ocean that we just looked at, and just go ahead and make them idealized, perfectly straight. Whereas in the ocean, they weren't perfectly straight, but they were pretty straight. And evenly spaced apart, which the waves in the ocean, they did look pretty evenly spaced. Again, they're moving to the right. And so, my wonderful students, this is what Sir Isaac Newton would have predicted. Because Sir Isaac Newton did not think of light as a wave. Sir Isaac Newton, he had a lot of optical principles that he figured out. He wrote a whole book on optics. And he's the one that figured out, that sunlight, the prism, all the different colors, the rainbow. He's the one that began the process of everybody figuring that out. But he thought of light as little particles, little teeny BBs, little particles of light, going from point A to point B and ricocheting like a billiard ball or a baseball, and then changing its path and then going off in the new direction. He didn't think of it as a wave. So if light really is, so go ahead and make a note. If light really is a particle, this is what you'll see. A shadow and only a shadow. So as you move from, if you're over here on the right side of the screen and you start at the top, you'll go from an area where there's light, and then down in the middle of the page, move downward, you'll be in the shadow, and then keep moving downward, you'll be in the light again. All right, now that's what Sir Isaac Newton would have predicted. And guess what? Sunlight does cast a shadow. All right? But what if this baseball is a lot smaller? What if it's nearly the size, what if it's maybe a few hundred or a few thousand nanometers across? Then you get diffraction. You get diffraction around the edges. All right? So it depends on the wavelength. And this wavelength looks good to produce diffraction. So here's what it will look like. And I've just put two little zones of diffraction at the very top and bottom of the baseball. But you can think of, entire areas where the wavelets generated at the edge of the baseball, at the top edge of the baseball and down at the bottom edge of the baseball, they form, they convert those straight up and down waves, the flat waves coming in, they convert them into wavelets that generate spherical waves like this. All right, now notice, my wonderful students, that light is sneaking behind the baseball. Let me repeat that because it's very important. Light is going around the corner. It's getting behind the baseball where Sir Isaac Newton would have said, "No way, Jose. No way, Jose." There's no light back there. It's only a shadow. And you might think to yourself, Dr. B, how can light propagate into a shadow? If light propagates into the shadow, that means it's no longer a shadow. It's lit up. And my wonderful students, the answer to that is it does. And it forms a bright... Now, if you put a piece of photographic film right back here by this dot back here, yep, you would photograph a bright dot in the middle of the shadow. And that dot is known as Poisson's dot. And Poisson and a bunch of French scientists were trying to figure all this wave theory of light out. And I believe it's back in the 1800s. And they said, all right, well, if light really is a wave, and if it does diffract, and I think what Poisson said is, Poisson figured out that this was possible, and he said, that means light cannot be a wave because this is not possible. But then somebody said, yeah, I measured it, I observed it, I photographed it. They photographed Poisson's dot. It's true. And I will give you some study homework tonight about Poisson's dot. You can read about it. Very interesting story. And so, as I mentioned last time, the idea of a wave being a transporter of momentum and energy is correct. I mean, if you put a photographic plate back there, the energy and momentum it deposits into the photographic emulsion will turn the photographic emulsion into a new color. And when you develop it, you'll get an image there. If there was no energy, the photographic emulsion would come back blank. And they have photographed this. Matter of fact, it's easy. It's relatively easy to photograph if you have a laser. You know, even one of these little cheap red lasers, you can do it if you set it up right. So the whole idea is that waves and particles, Newtonian particles, Sir Isaac Newton, F equals ma particles, they're fine. The baseball, we know what it does. Goes from point A to point B on a parabola maybe. You know, F equals ma. F delta T equals delta P. F delta X equals delta KE, the work. All that stuff works nicely for baseballs. Much more difficult for waves, but we have a way of figuring out what waves do. Waves interact with matter like a baseball, a spherical piece of matter, significantly differently than a million little bullets. You know, so if you have this baseball and you send a stream of little BBs past it, they'll cast a shadow. There'll be a zone where you're safe from BBs. Okay? But if you send light past this baseball, nope. There's a bright dot. You won't be safe from light. Light will shine into the darkness. And that's what we call Poisson's dot. Now, that is waves interacting with solid matter. In this case, a sphere. Very unusual. But now here's another, for those of you that are on your cell phone. Okay? And around the, good, thank you. we have another topic that we want to talk about, and that is waves interacting with waves. Now this is something, and actually I already mentioned it, but I want to go into this idea of waves interacting with waves. It's the generic term for that is interference. Okay? Waves interfere with waves. Matter of fact, in an atom, in a nucleus, in a molecule, waves interact with each other. It's really interesting. That's quantum mechanics. So let's go through some of the concepts of wave interference. Okay, so let's start with two sources of waves. And let's say that the waves move out independently. And at certain points, as I've mentioned before, you might have two wave crests meeting for a super big surf or a rogue wave if it's out in the middle of the ocean. And it could swamp a big freighter or a tanker if the wave's the right size, the right place, the right speed, and everything like that. But at other points, you get two troughs that meet, and then the trough is extra deep. Okay? Now, those two situations, peak to peak, trough to trough, from two different sources, are what we call constructive interference. All right? So if you're looking at waves in the ocean, say there's a storm off the coast of West Africa and a storm off the coast of Nova Scotia, the other side of the Atlantic, somewhere near Bermuda or something, those waves are going to interact. You know, each storm will produce waves. You know, the storm off West Africa will send waves to the west and to the northwest. Storm off the coast of Nova Scotia will send long-distance waves to the southeast, towards Bermuda. Okay, they'll meet somewhere in the middle, and at a certain point, at a certain time, you'll get two crests that meet, and then you'll be way up there. If you're in a rowboat out there, you'll be way at the top of that wave, all right? But then if you don't move, a second later, you'll be down at the bottom of the trough. And you'll see all the water like walls, left and right of you, front and back of you, you know, depending on how your rowboat is directed, all right? And then a second later, you'll be back up on top of the crest, a super high crest. And then a second after that, you'll be, whoa, down at the bottom of the trough, a super deep trough, all right? Now, to the left and to the right of you, those points, when you're at the top of the trough, those points might have a different interference state. Okay, to the left and to the right, to the front and to the back of you. Depends on the shape of the waves. So if at these other points to the left and right of you, or to the front and back of you, if it's a point where a crest meets a trough, and that's going to happen all over the ocean, where that happens, the two waves, you get basically flat water, no wave. And that is what we call destructive interference. All right? And so if you're in a rowboat, and you're at the top of the wave, then in one wave period, you'll be back at the top of the next constructive interference. And after half of a period, you'll be down at the bottom of the trough, and that's constructive interference. But a quarter of the way through the period, you'll be at a place where a peak from West Africa is interacting with a trough from Nova Scotia, flat water. So you'll be back to sea level just for that instant. So, and if you think about it, if you're out there in the ocean, you're going from the peak to sea level, down to the trough, back up to sea level, back up to the peak, back down to sea level, back down to the trough, back up to sea level, back up to the next peak, and so on and so forth, as long as those waves interact where you're located. All right? Now, somebody that's one full wavelength, here's another thing you can make a note of. Someone who is one full wavelength away from you, he'll be at the same level as you. You'll be going up and down together. You know, you might not see him when you're at the bottom of the trough, but when you get back up to the top, you'll be, hey, buddy, you know. You can throw, you know, something across to him and he catch it. But then you're back down. Now, if you're half a wavelength away, you know, here's how it's going to, if you're half a wavelength, it's going to be topsy-turvy. You know, you're at the top of the peak, your friend's at the bottom of the trough, and then, it's going like this. You know, half a wavelength away. You're up on top, he's down in the trough. You're in the trough, he's up on the, so if you want to get seasick, that's the combination you want to try to focus on. All right, those two guys are going to get, if they keep an eye on each other, you know, if they're half a wavelength away, they'll be able to see each other the whole time. And tracking their buddy, can you imagine 30-foot waves? And you're watching your buddy going up, and while he's going up, you're going down. And you're going to, I hate to say it, but almost anybody in this room, I'll bet, would get really dizzy just watching the other guy, and maybe even, I don't want to say it, but, you know, you might even lose your lunch, you know, because seasick, you can get really seasick that way. Anyway, to rephrase it, out in the middle of the ocean, two storms, two sources, there'll be locations that are out of synchronization by half a phase. You know, peak and trough are out of phase. But one wavelength away, they're in phase. Trough, peak, together. Trough, peak, together. And then half a wavelength away, peak and trough, trough and peak. Peak and trough, trough and peak. So the location and time are critical for understanding the constructive and destructive interference. So you can get constructive and destructive interference at any point. Just depends on when when you're making your observation. Now let's take a look at this. All right, here's a diagram, and this is a really simplified diagram. You can sketch this one. Two waves, one from West Africa, one from Nova Scotia, heading toward each other. Now, in the ocean, waves are not quite that shape, but this is kind of an idealized view, right? And they're going in opposite directions. Now, at that location, where my cursor is here, right in the middle of the screen, those two waves are going to form a rogue wave, a big, huge crest. Okay, so that's the double. But then what happens after that? Well, the waves are interfering with each other. They're interacting with each other. But do they bounce off each other? I mean, that's what baseballs would do, or BBs, or billiard balls. You know, they both come in from opposite directions. They interact, and, you know, if you've ever played pool, you know, the balls bounce back the other way, unless you kind of hit it at an angle. But if they meet head to head, then they'll go back the other way. Does that happen with waves? No. Because here's what happens with wave. Wave B just plows right on through. Wave A, wave B was started up in Nova Scotia, and it just keeps rotating. Wave A was started down in West Africa, and it just keeps rotating on up towards Nova Scotia. And the one from Nova Scotia, it just keeps moseying its way down to West Africa. And they interact, and they got a crest, big supercrest. And then you just keep going. This would not, as I said before, this would not happen with a baseball or a set of baseballs or a set of billiard balls or a set of BBs or anything like that. Newtonian particles do not do this. And here's the interesting thing. Waves in the ocean are made up of molecules that we think of as Newtonian particles. You know, F equals ma for water molecules. Yeah, we can figure that stuff out. A little bit of trig, a little bit of calculus, a little bit of stats. Yeah, we can hack it. But the wave behavior definitely is not the behavior of a particle. All right. Destructive. Now, side note. Turn these diagrams upside down and you have a deep trough constructive interference. So go ahead and make a note of that. So if you have the upside down version of the top diagram here, okay, two troughs coming toward each other, they'll form an upside down version of that lower image. Okay? All right, and then they'll move off. They'll move off. I messed this up. They'll keep moving off as troughs. Okay, the upside down version of this lower image. All right, now let's talk about destructive interference. All right, so here's a trough and a peak, a trough and a crest. And again, this is kind of idealized just to emphasize the destructive interference concept. Where they interact, right here in the middle of the screen where my cursor is, A plus B add together, but one of them's above sea level, the other one's below sea level, so when they add together, you get zip zap. You're at sea level, flat water, my friend. Zero amplitude. But just for that 1 second. If you take a snapshot right there, you'll think, oh, nice calm day. But a second later, those two babies are moving off from each other. All right? And the one from Nova Scotia, it's heading on down. The trough from Nova Scotia is heading on down to West Africa. And that trough from West Africa, or the crest from West Africa, it just keeps heading on up to Nova Scotia. You know, and now in a real ocean, with real ocean waves, you're getting both troughs and crests, and you're getting not just two, you're getting bunches of them. So you're continually oscillating between, as I said, a super big peak, sea level, and a super deep trough, and then back to sea level, and then back up to the super tall crest. All right? And that's what interference is about. Now, this is a one-dimensional wave picture, right? So I just want to emphasize that. And real waves are actually three-dimensional, plus time. So you can see, you know, the whole idea of space-time is space and time being treated as dimensions, not as, you know, time as something different from a spatial dimension. You gotta do both. You have to treat both as closely, as similar as you possibly can. Now, so that's the basics of waves, constructive and destructive interference. Now, I want to describe another interference effect that is important for many students around the world who have cars to understand about. Now, I know that you are all very nice young men and women, and you never break the speed law or anything like that, so you've never had to interact with this guy. You know what? I have been seeing a lot of traffic police. I have cruise control in my car, so I never get speeding tickets anymore. I get other tickets, but I don't get speeding tickets. But I every morning on Chapman Road, where I drive to school, early in the morning, you know, like 6:37 when I drive in, there's always a cop waiting You know, they're not doing anything. You can't see what they're doing, but they ain't moving. They're just parked by the side of the road, and they're waiting for people that break speed laws, which I know you are nice young men and women. You don't do it. But what they do is they use the phenomenon of beats. Okay? And Thursday, I'll give you a demonstration of beats. And unfortunately, I should have done a demonstration of it today. But, so what beats are two sets of waves, but slightly different wavelengths. Right now, look at those two upper waves. Okay? This one at the top has a slightly shorter wavelength. Okay? Up here, this one. Okay, so there's more of them. There's more crests. There's one here behind the word beats. Then there's another one here in the middle of the screen. That's 3. Then there's another one here, 4. And there's another one here at the right edge of the screen. That's 5. Now the one down below, it's a bigger wavelength. Okay? It's got 4 peaks. You can see them just looking at it. All right, so it's a longer wavelength. Now they're close. One of them's about 25% different wavelength. The big one, it's 25% more. All right? Now what that means is that if you're in the rowboat, right here at the left side of the image, your rowboat's up there on top of that wave crest. But then if your friend is in a rowboat here, he doesn't get jack because the trough of the second wave corresponds to the peak of the first wave. So you're getting pretty close to flat water. But then when you're back out here at the other side here, you're back to a constructive interference. So here's what we're trying to say. You know, the previous example, we didn't really have a wavelength. We were just talking about waves in the ocean. This one, if the wavelengths are similar, just one of them a little bit longer, if the frequency is a little bit different, you know, a little bit higher frequency, not too high, you know, not like 3 times as high, not a third of the wavelength, but, you know, like 110% of the wavelength, 110% of the frequency. Okay, so small difference, you'll get this. Okay, now if these were sound waves, my wonderful students, and they're moving towards the right, you know, from left to right, here's what you would see. You would see high pressure here. Look at this. Look. Come on, look. Look. Yeah, thank you. Look, everybody. Come on. What am I, just whistling Dixie up here? This is where you're going to get high pressure. Your eardrum will respond to that. Your eardrum's not going to respond to this. That's pretty low. It's like flat water. But then it's going to respond to this. So what that means is you hear it as a low frequency sound. You know? It'll be like a rumble or a beat. Right? Now, actually, I'll tell you that, you know what I'll do for homework? There's some YouTubes of demonstrations of beats, and I think Darian, don't we have one of you actually doing beats? In this room, or maybe the other room at the other end of the hall. So I'll put those up for you. I'll point those out to you. You can actually listen to it. You'll hear the beats using 2 tuning forks. One of them slightly different. And so that's what you hear. Now here's a little bit more exact picture. I don't like that previous one. This is my design here. So here are your 2. Look at this, the black one and the red one. Okay, now let's count the number of waves. Okay, they both start out here on the left. The black one, 1, 2, 3, 4, 5, 6, 7, 8, 9 peaks. Now the one on the red one, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So what was the first one? 9? Okay, so 9 and 10. All right, so the wavelengths are close, and if you just look at them, they look pretty, they look about the same, but they're not. And if you were listening to sound waves of this frequency and sound waves of this frequency, and they both arrive at your ear, so if they're in the same room and they both mix together, you're going to get beats. Okay? So slightly different frequencies, slightly different wavelengths. Now the way to calculate the frequency of the beat, all right, I told you it might sound like a rumble or a rattle, a low frequency, and you'd hear it. You know what else? I think sometimes you hear, if you have stinky speakers in your vehicle, they really rattle. Part of that is from beats, if they're cheap speakers. So the way that you figure out the frequency is F1 minus F2, or F2 minus F1, whichever is bigger minus little. Okay, and these two sound waves, one of them's a smaller wavelength, the red one, the second one, that's smaller wavelength, more waves in the same distance. Black one's a little bit larger wavelength, so the smaller frequency is the top wave, the higher frequency. So if these were sound waves, one would sound a little sharp relative to the other. The red one would sound sharp, or the black one would sound flat. I mean, if the red is on key, the black one would sound a little flat. If the black one was on key, the red one would sound a little sharp. All right? So the way you figure out the beat frequencies, just subtract. So figure out the frequencies. V equals lambda F. Figure out each one, and then subtract. All right? Now, here's my equilibrium lines. Okay? So your pressure variations are high pressure, low pressure, relative to equilibrium, or ambient air pressure. Now, for this one, I made up an imaginary wave speed of 80 meters per second. Go ahead and write that down. All right? So the speed of sound in this medium, so this is on another planet with a different atmosphere, V equals 80 meters per second. Now, I set up the two frequencies to be 106.7 hertz for the black one, the first one on top, and 119.5 hertz for the one on the bottom. All right, so you can figure out the beat frequency. F2 minus F1, easy. It's just a few cycles per second. Now, when you add those two sounds together on this other planet where the speed of sound is 80 meters per second, that is what you hear. That's the sum of the two sources. All right, so this is you out in the middle of the ocean, but now there's two different wavelengths meeting where you are located in your rowboat. All right? Or this is you listening to somebody with a guitar that's in tune and somebody whose guitar is just a little bit out of tune. All right? Or somebody with a tuning fork that's right on the money, and somebody whose tuning fork got banged, and so it's not quite at the right frequency. All right, so it's a little sharp maybe. And so this is what you hear, the sum of the two. All right? Now here's the sound, the loudness is proportional to the square of the amplitude. So this is where it's loud. Right here. This is where it's faint. Now, if this were out in the ocean, right there in the middle would be flat water. And over here would be a big crest and deep troughs. And here it is loud over here. All right? You can see that peak and peak, trough and trough meet again out here. But over here in the middle, where the sound is faint, it's peak meeting trough approximately. So it's flat water or very low amplitude. So if it's a sound wave, it dims out. So you go loud, dim, ba, 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 but much faster than that. Okay? And so that's what you get with beats. So in this case, the beat frequency is 12.8. Okay? And you can figure out the beat wavelength, 6.25. Here it is. Between two successive loud parts. All right? Now, what the police do is they do the same thing. And they measure the beat frequency, because here's what happens. When they send out a radar, they know the frequency that they send out from their radar gun. But when it comes back, if you're in motion, the Doppler effect will change the pitch slightly. So if you're moving toward the policeman, the pitch or the frequency of the radar will be a little bit higher, a little sharp. If you're moving away, it'll be a little bit lower. It'll be a little flat. And what they do is they compute the beat frequency. And then from that, and I'll show you on Thursday next week, I'll show you the formula for getting that. It's kind of fancy looking formula, but from that beat frequency, they figure out your speed. And so they know if you're speeding or not. And I got a speeding, last time I got a speeding ticket, I was going 70 in a 45. I was trying to get my son to school on time. That's before I started using cruise control. Anyways, my son's in college now, so he has to get to school on his own. I don't get any more tickets. Anyways, I was doing 70 to 45, and and you know what? Here's the other thing. He was right behind me in an unmarked car. I thought it was a convoy. He was right behind me. It matches speed for speed. I thought, all right, let's go through these lights. But it was really a cop car. He didn't have any. And then finally, when we got near the next stoplight, he started running his lights. And I thought, oh, sugar. This guy ain't my buddy. We ain't in a convoy. He's a cop. Oh, man. Now, so beats, speeders, I'll give you some homework about that. Now, last comment of today. Where we are going with all this wave stuff, we are heading to the periodic table, my friends. And we will hit the periodic table on Thursday next week, but Tuesday, exam 3. All right, I'll see you then. Everything up to beats. And so there'll be some homework tonight. There's going to be a big homework tonight, too. So you have some extra practice. What? Everything we did today is going to be on the exam. That's correct. Hey, Jackie.
So basically, I remember when...
Hold on. Let me terminate the...